Thank you for coming to this Tech Competency Lab. I'm Sebastian Benthal. I'm a fellow at the Information Law Institute, and I'll be teaching you today about code as society. This is a data-driven investigation into software infrastructure and software security and risk management. That's geared towards primarily non-technical students, to get them to understand some of what's at stake with cybersecurity and the vast software ecosystem that many of your applications and products are running on. So in many ways, this is a presentation about software updates. As a consumer, you probably see messages like this and don't give it much thought. Things like your smartphone or even your IoT devices are getting software updates all the time. But I want to, for the purpose of this presentation, invite you to think about how software is produced and where the software updates are coming from and why they're significant from a sort of social and policy perspective. And I just want to remind you that please feel free to ask questions in the group chat if anything comes up that you'd like me to clarify during this talk. So if you're involved in writing software, you may or may not know that your software is divided up into packages. And when you're writing software, very often you'll write at the top of a piece of code, import such and such. And these are the package import statements, and any piece of code is going to depend on so many other packages. And this is true across many, many different programming languages and ecosystems, including Python, Ruby, JavaScript, Java. And these packages are going to be referenced by a version number. You might see these version numbers in software updates that are consumer facing, but there's a kind of convention for marking the updates of software packages called semantic versioning, which is quite widely used. And the leftmost number indicates a major version. And basically, the smaller the number, the more rightwards the number, the more precise or minor the changes. And this is an important signal for software developers, because if you depend on a package, then you know that if there's a major version change, then something about your expectations about how that software works kind of under the hood have changed. And you're probably going to have to change what you've worked on to adapt to that. So this is a way of communicating kind of upstream, from upstream, what downstream users' expectations should be. And software development is often quite complex in that the software is being developed in many different parallel branches at once. So because you might be using, as a consumer-facing way, if you were using like an old version of Windows or the Apple iOS system, that old version might still be getting updated even while a new version was available. And so there's this complex branching structure to the way software gets updated. And this has a lot of interesting implications for the ongoing risk management and maintenance of software. The idea of supply chain risk is something that we're probably maybe more familiar now than ever because of COVID. If there's a shortage of labor or a factory breaks down or something, we call that in sort of the broader industrial setting supply chain risk. And there's similar but not identical logics happening in software production. So in cybersecurity, for example, if you have this nested set of components that all depend on each other, a vulnerability in a low-level component will quite likely affect a higher-level component. So, there's a really an example that made a lot of news was in 2014. You might remember news about the Heartbleed bug. OpenSSL, it was a software library for secure networking used in a wide variety of web servers. It was more or less ubiquitous. And they discovered in 2014 a bug that allowed people to steal data from any software using this package, OpenSSL. Um, as a aside for the policy people, Heartbleed bug has this ID CVE 2014 0160. You might be interested in where that's coming from. So there in the U.S. has something called the National Vulnerability Database, which is maintained by MITRE in a kind of public-private partnership with input from the DoD, and it's a database of discovered technical vulnerabilities, which assigns to each vulnerability an ID. And this is set up to facilitate data sharing between various parties, including vendors and users and security experts, as a sort of cooperative policy solution. And it's as an institution, it's an important one for cybersecurity, and it's also one that is widely critiqued by practitioners in the field. There's all sorts of problems. I'd love to talk to you more about National Vulnerability Database, but the important thing for this talk is that it's what's tracking and labeling the discovery of publicly known software vulnerabilities and also hardware vulnerabilities and others. So another example of this exact kind of supply chain risk was the Equifax breach in 2017. So even though this keeps happening, people haven't solved this problem yet. And so the Equifax attack, where hackers stole 200,000 credit card accounts, exploited a different vulnerability. And an interesting thing about that vulnerability is that it had been known about for 2 months and already fixed in one version of Apache Struts, which was the underlying dependency. But Equifax had not updated their own software because upgrading that component is costly. There was perhaps an API breaking change, and they would have had to change their own tools that they built on top of the software if they had taken on this older update. So what you get with software supply chain management is this constant tension between accepting the upstream changes, which might destabilize your functionality, or they might introduce new problems, but they might also solve old problems and maybe bugs you didn't even know about. Or you could not accept that upstream functionality, and that exposes you to different kinds of risks. So, so part of the reason why cybersecurity is so hard is that people don't know how to manage this relationship with their own infrastructure. So I found that it's helpful sometimes to think about sort of two dimensions about the way a piece of software could be vulnerable or sort of risky. If you think about robustness and fragility as kind of a static amount of technical ability to be attacked, like a house of cards, is very fragile, and the Death Star, if you remember from the original Star Wars, it was very massive and complex and powerful and very hard to defeat. It did have one important vulnerability, which when attacked, caused the whole thing to explode. And so it, in that sense, it's quite brittle. It didn't have a way to respond to being attacked in its, small attack surface, or what was available as an attack surface. Whereas if you consider like Iron Man's suit, I believe that's powered by nanorobots, and anytime it gets damaged, it heals itself. And ideally, you would like some aspect of your software supply chain to be not only robust, not having a lot of vulnerabilities right now, but resilient, so that if someone discovers some problem with it, it heals itself. And of course, you could have something that is constantly healing itself, but still full of vulnerabilities, and that would also be rather unreliable. So it's really, you want to get the best of both worlds. And the question is like, how would you ever get that? And this is challenging because software vulnerabilities are not obvious things to find. I mean, generally, if you have a security vulnerability in some software, it's because something has been overlooked by the people working on. But you know, software is always very complex, and people are always overlooking things all the time, like from the moment that it's been written. So really, there's been a lot of work in trying to come up with a kind of scientific modeling process for vulnerability discovery. And there's one interesting one proposed by Al-Hazmi and Malaya that they've shown to be quite empirically robust. And basically, it's a sigmoid function. There's a slow learning phase and a steady linear phase, and then a saturation phase. So it looks something like this. And the idea is that you know, we are saturated when all the vulnerabilities that are in the software have been discovered. You know, someone writes some software, there's some set of vulnerabilities in them, and they're unknown. And it's only once the software gets sort of uptake and gets invested in that that the rate at which those vulnerabilities are discovered increases. And then after some phase of, you know, common usage, most of the vulnerabilities get discovered and it plateaus. And they showed that this applies to operating systems and web browsers, a number of other pieces of software. So this is what it looks like for OpenSSL. And it's an interesting and I think revealing picture. So on the x-axis here is time, and the y-axis here is the number of CVEs, that's vulnerabilities in the National Vulnerability Database, for this software package that have been fixed. And so what you can see is, you know, if you think about the sigmoid function, this sort of S-shaped curve, I don't know if you would agree with me, but the way I read this is that for version 0.98, it looks like a sigmoid function with a, you know, a slow uptake up until about 2009, then sort of linear with a bunch of lumps, progress until about 2012, and then it flattens out again right up through to 2014. And similarly with version 1.0, a sort of roughly S-shaped curve through to 2014. And then of course, 2014, that's when Heartbleed gets discovered. And suddenly the rate at which the vulnerabilities are getting fixed is going way up. And what that suggests is that there's something a little bit wrong with the Hazmi-Malaya model, because it has a second linear phase. And, you know, I think socially we can intuit what's going on. They underinvested. They stopped looking for new vulnerabilities, and they thought they had found everything that they needed to. And that's what made it risky to use. The belief that it was secure meant that it was so widely used that it became such a big deal when the vulnerability was discovered. They realized that they had underinvested. So another way to look at this, which is revealing, is to say the number of vulnerabilities in the OpenSSL versions over time. So this is a little bit inverted, and this is a tricky graph to show because you got to note that this is always only the vulnerabilities that are in the National Vulnerability Database. So this data could be totally wrong, especially if, I got a question from Dylan.
Yeah, I just put it in chat, so I wasn't sure in terms of order of operations there.
Yeah, thank you. Yeah, so that's a really good question. So the question is the idea of saturation theoretical? Is it possible to discover all vulnerabilities for a given software? Um, I think the answer is that that it is possible for software, a piece of software, to not have any security vulnerabilities in it.
Okay, that was exactly my question. Yeah.
Yes, yeah, but there's a lot of really interesting kind of computer science, basic computer science around this. So one thing that is impossible is to say have a program which in general can look at another piece of software and determine whether or not it has any vulnerabilities in it. And so the problem is, saturation is as an objective fact about a piece of software, could be true, but as an epistemic fact about software, uh, for most, suitably complex software, it's basically impossible to know that you've saturated. Um, and there's a lot of very interesting kind of foundational mathematical reasons for that. Um, but that's part of what's making this discovery process so hard. It's so the question of like how do you know when you've looked enough is a terribly difficult problem. Um, and it and just to move back, thanks for that question. That was great. The if you look at this vulnerabilities to the OpenSSL versions over time, one thing that sticks out is this is sort of the previous chart turned upside down in that it's number of vulnerabilities once they were introduced into the software, and then how they were remediated over time with subsequent versions. So here 098 had roughly 60 vulnerabilities in it right up until so the beginning of 2010, at which point they started really fixing them. But what I want to point out for this chart is that the next version 1.0, actually started out with even more vulnerabilities than the 098 version. And same with the 101 version. So as people made changes, I should say the OpenSSL did not use strict semantic versioning in this case. So these patches are actually much more significant changes than the semantic versioning schema would suggest. So each of these really introduced quite a bit more code. And so you can see that as they introduced more code into the library, they introduced even more vulnerabilities and then had to kind of work them off over time. So this question of, do you use the more recent version of the software, or do you wait for it to have matured or been, had some of the bugs worked out, is a real one if you're trying to manage cybersecurity risks, say, in a business or in a government. And so the take-home messages about this is that the AML model is helpful as a kind of construct, but it's definitely sort of a theoretical model, and this sort of exception that proves the rule with OpenSSL of like a false discovery plateau was because people sort of incorrectly believe that it reached saturation. But the other point I want to make is that that sort of social belief that that the software was secure, even though it wasn't, was not like a technical property of the software. Whereas like robustness in terms of like an absence of technical vulnerabilities might be a technical property of the software. Resilience, the ability to be responsive or be to have people really monitoring or look up, that's a social property. That's a property of the whatever people are touching and working with that code. And so an interesting part of this cybersecurity risk analysis is it's really a social science on a lot of levels. And because this is, I've been learning a lot about infrastructure studies through my work with Thomas and Angelina and the GGLT people and Benedict. And it's very interesting to think about the way this piece of critical digital infrastructure uh, was depended on, thought to be robust until it was broken. This is a, um, but its maintenance. You know, if you're talking about maintenance of this infrastructure, it's not that the lack of maintenance led to new vulnerabilities. It's not like if you don't maintain a physical building that it might deteriorate over time. Really, it was a lack of investment given the software's growing infrastructural importance. Um, and so the vulnerability side of the equation is only one part of the risk analysis. You also have to think about the exposure. Like, what does it mean for a software library to be used by many other applications and services? And that's what this next piece of research uh, goes to explain. So just to recap, so programming language has a number of software packages written into it, and those are connected to each other through import statements or requirements. Another word for this is a manifest. And the risk for a package is partly a function of the community's resilience, how much it's investing in its own robustness, and also how widely it's used. Um, and just by analogy to make this a little bit more concrete, there's an analogous thing that happens in disaster risk reduction. So if you're trying to calculate how risky, how much risk there is in different regions to some kind of natural hazard, like a tsunami or an earthquake, um, you there's a fact, an interesting fact. So around 2008, you might remember there was a terrible earthquake in Haiti and another earthquake in Santiago, Chile. And the earthquake in Santiago, Chile was actually a bigger earthquake. It was higher on the Richter scale or whatever. But the earthquake in Haiti was much more damaging. And the reason why is that the infrastructure, the architecture, the buildings in Haiti were much more vulnerable to the earthquake. Um, so the way, some World Bank and other disaster risk modelers run these calculations, they say, okay, what's the magnitude of the hazard? And what's the exposure? What's the amount of stuff that could be affected by it? And then how vulnerable is that stuff that might be affected by it? And by combining those, you get a sense of the risk, which would tell you the kind of investment that you would want in that sort of infrastructure. And there's a similar kind of equation that comes from supply chain analysis. You say there's threats and vulnerability, and then the consequences to the vulnerability being attacked by the threat. And for the purposes of this presentation, I'm just going to abstract away threats into a generalized, uniform field of danger, which is, definitely a simplifying assumption, but it's to demonstrate something. But if we're talking just about the exposure and sort of the consequences and the fragility of a piece of software, then we can start really pulling data into this. So if we talk about the exposure of a package as the number of times it's been downloaded, and that's just a proxy, but that's an indicator of how much a piece of software is being used, right? Because the package exists at sort of the abstract level of a piece of software, and in order for it to actually be run anywhere, it has to be downloaded, it has to be deployed on some server or onto your smartphone or something. And then for fragility, we're going to make a simplifying assumption. We're just going to assume that fragility goes down with each subsequent release. So we can say fragility is 1 over the number of releases of a package. And so we can get this risk metric to say, okay, the number of downloads divided by the number of releases is some indicator, maybe it's proportional to the risk for that package. So that's a first step. And then the second step is to say, well, but these software packages are aligned in some kind of a dependency or supply chain. And so the vulnerabilities are going to propagate up. So a package that a lot of things depend on, if it has a vulnerability, then everything that depends on it is going to inherit that vulnerability up. But a package that is widely used is very exposed, and so it's going to sort of deliver that exposure down to its dependencies. So an example might be, the Apache web server, which I don't know its market share right now, but it used to be behind something like 60% of the websites you would ever go to use the Apache web server. Also used as a component OpenSSL. So OpenSSL, if it has a vulnerability, winds up affecting all the Apache web server instances. Apache web server is in 60% of the websites, and you can do the math. That's why OpenSSL and Heartbleed was such a big deal. So if exposure is propagating to the core, and I don't know if these diagrams are going to help, but if you imagine sort of this is a network, and these are the values. If you say the size here of the nodes is the value of that node, and that node propagates through those links, then exposure is going to concentrate in the core, and vulnerability is going to propagate out to the periphery. And if you say something like on the left, if you say size is proportional to exposure, and then color warmth is proportional to vulnerability. This is sort of a randomly generated chart. It's going to, if you do the propagation, and on the right, color warmth is total risk. So you can see that it's the core components that have a lot of dependencies on them that are where you would want to concentrate your investment if you're trying to figure out how to maintain or secure the system. And once you have that set up, you can run this on the real data. So this is on the total Python ecosystem, right? And like purple is secure or less risky, and red is risky here. And so if you run this analysis, you wind up getting a pretty dramatic result. And it just so happens that the software packages involved here, one is called, one very risky package is called 6. 6 is sort of interesting in light of the preceding discussion, because it's a package that's supposed to, it's something that if you're using the old version of Python, Python 2, and you want to use a Python 2 package in a Python 3 application, then you can kind of wrap it in 6. So 6 is kind of a duct tape solution to fixing the problem of software not being maintained. But that piece of duct tape is not very secure, because people aren't updating it very much, but apparently a lot of people are depending on it. So if there was some sort of security issue with that conversion, a lot of things might be at risk there. And the other thing here is Zopenplone, which is a I don't know if you're familiar with the idea of a content management system, but Zopenplone were ways that was a set of software that people used to make websites, 10 or 15 years ago, that at some point got a lot of uptake and a lot of interest, and then the community kind of died off and stopped maintaining it. And so they've had a post on their website for a long time saying, this is not really an actively maintained piece of software anymore. We don't recommend using it, but a lot of people still do. And there's a lot of kind of legacy systems. Maybe last time I checked, like one of the public-facing websites of the CIA was still built on clones. It's often when you build something into infrastructure, it takes a long time for it to go away or be replaced, and that's where a lot of this cyber risk comes in. So real software is quite a bit more complex than what I've presented, and that you know, the version dependencies change. So version 0.1 of the piece of software of software A might depend on version 0.1 of software B, and then you know, version 3 of A might depend on version 3 of B, but it doesn't always line up directly. So there's certainly a lot more work that can be done in this kind of analysis to make it more realistic. But the main things I wanted to kind of convey to you in this talk is that we're often, especially as users and consumers, just encourage these software as like a technical artifact or a commodity. But if you do like a very careful data-driven investigation, it reveals that software is really social structure. There's two very important non-technical aspects to the risk to you and institutions as a consumer of software. And one of those is the sort of vibrancy of the software development community. And another is the kind of relationships between packages and other packages, which is to some extent a technical relationship, but it's also a social one. It's saying this group of people has trusted this other group of people to develop and maintain this kind of logic, core logic that they depend on. And so, especially to lawyers and other people like that, it might be useful sometimes to think of software as a complex, interconnected set of institutions rather than as a production line, sort of building parts. And that's all I have for the presentation. These are the two references. These are a couple of publications that the empirical work for this is based on. And with that, I'm really happy to talk more about this with you. Thanks for listening.